Why do people go bald?
Why are baboons' bums red?
What's a light year? Why do leaves go brown in the autumn? Why do monkeys like bananas? Why do some things glow in the dark? Why do animals not understand you? Why do my receipts fade after a year?
Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientists with me, Sue Marchant, and Dave Ansell. Now, we have lots of questions coming in, so we'll start with one that's come in by the text this time. It says, do stars inadvertently explode, or are they harmless? And that's from M. Oh, must be 007. Thank you, M.
Not quite sure what she means by inadvertently. Stars do explode sometimes. You can predict it tends to be near the end of their lifetime. There's a star relatively near to us, maybe about 600 light years away from us, called Betelgeuse, which is a very, very large star. It was originally an incredibly bright white star, burning hydrogen into helium. And then it sort of ran out of hydrogen and it couldn't burn anymore, so it cooled down and collapsed a bit, and then it started burning helium, so it expanded a lot and it sort of blew off the surface, and at the moment it's a big red giant. It might be burning helium or carbon, or there's various different materials in which it might be burning. Eventually it runs out of elements which it can burn. This isn't burning in the case of lighting a match, this is burning in the case of nuclear fusion, so you're kind of gluing these elements together into making heavier and heavier elements, which releases an immense amount of energy. But eventually it runs out of things it can burn, and it just collapses to form a neutron star, and that releases an immense amount of energy, sort of equals mc squared, and it releases about a tenth of its mass. Einstein worked out, so a tenth of its mass is an immense amount of energy, and it will produce an immense bang when it does go off. I talked about it a few weeks ago. So stars do explode, particularly the big ones. Even the sun might go off with a fairly small bang, but nothing like that. But you can predict it's always at the end of their lifetime. There's something like the sun is going to be very, very stable for the next several billion years. So they do go off bang, but you have some idea of predicting roughly when they're going to go off.
And they're harmless or harmful?
Depends how close you are to them. Betelgeuse going off, if that went off bang, where we are now, 600 light years away, it would be impressive in the sky. It would be as bright as the full moon is, just a single point. And you'd be able to walk around in the middle of the night if Betelgeuse was up. Even if there wasn't a moon, it would be that bright. But it's probably not going to do us any harm. If it was, say, 50 light years away and you get huge amounts of radiation, it could do odd things to the atmosphere. If you're very, very close to these big explosions called supernovae, if you're close to a big supernovae, it could even wipe out life on the Earth, because you'd get so much radiation hitting the Earth.
Crikey.
But they're very rare.
Oh, well, that's something. Dr. Dave from The Naked Scientists in the studio, and right now we want to go to the phones and say good evening to Alan. Hello, Alan.
Hello, Sue.
Hello there, you're through to Dr. Dave.
Thank you. Hello, Dr. Dave.
Hello, Alan.
Nice to talk to you again.
Andy.
Basically, as long as I can describe this, then you understand it, we might get somewhere. Basically, it's about mobile phones. We've got mobile phones, and there's many different companies that produce them and operate the systems.
Yeah.
But at some point, they all communicate at a central point for us to make a call to another phone, which may not be of the same company. Is there a central point or computer that actually sorts out all those phones that are coming into it and redirects them to the phone that they're aiming for?
I don't think there's one computer in one place, but there's certainly a whole set of different ones. When you make a mobile phone call, essentially the signal gets converted into a radio signal, digital radio signal, sends the information about what you're saying to the mobile phone base station. The signal then gets put into an optical fibre. So you've basically got a flashing infrared light down a long piece of glass. That probably gets transferred around inside an optic fibre network for that carrier, so your mobile phone company. And then at various points, they'll have places where that connects in with other companies. And so I'm pretty sure there isn't just one, because if it went down, then the whole country would be in trouble. But there's probably order of 10 or 20 of them around the country.
But let's say, for instance, I'm going to make a phone call to Scotland.
Yeah.
Would that go through several different communication points? If it does, how can we speak so instantly?
It will certainly. It probably only goes between the carriers once, but it will go through lots and lots of different pieces of electronics between here and Scotland. And basically the reason why it's that instant is because everything works incredibly quickly. The information is being transferred by light, which travels at 300,000 kilometres a second. And that's a very small proportion of the delay. There is some delay, order of sort of hundredth of a second, maybe. If it gets anywhere near a tenth of a second, it's very hard to carry out a conversation. Yes, it will go through a few, and it's just the information just travels so quickly that you don't notice a delay.
Just finally, is it true that the waves or the radio waves or whatever it is from your phone are actually microwaves?
Yes. They're not quite the same frequency as your microwave at home, but basically microwave is a region of the electromagnetic spectrum. So light is part of the electromagnetic spectrum, radio waves are part of the electromagnetic spectrum. Mobile phones work in sort of 2-3 gigahertz, so that's a vibration of 2 or 3 billion times every second, and that's in the microwave region of the spectrum.
So you couldn't, if you had a load in the room all transmitting at once, it wouldn't cook a turkey?
If you, in theory, they're not a frequency which is absorbed by water quite as well as the ones which you use in a microwave oven, but it will get absorbed. And if you had enough in one place and they were all transmitting at the same time, then you could. But a mobile phone transmits at maybe 1 or 2 watts, whereas a microwave is 600 or 700 watts, so you'd need several hundred phones all in a very small space.
How scary is that? Don't try that at home, will you, Alan?
No.
In fact, there was sort of an internet scare recently whereby some advertising company had made it look like mobile phones could make popcorn pop. What they'd actually done is taken a microwave, taken it apart and put it under the desk, and then turned it on, so they were actually microwaving the popcorn on top of the desk, when it was nothing to do with the mobile phones at all.
Oh, well, there you go. Alan, thank you very much.
Thank you very much.
Take care, bye-bye.
Bye.
Now, this time to the email, and it says, hello, a few weeks ago you answered a science question for my big brother Ben. We listened to your programme in bed and love it. Hello, Ben and Toby. I've been thinking hard of a question I'd like to ask you, and I would like to know, what does fluoride in toothpaste do? I hope you know the answer, Dr. Dave. Love from Toby, who's age 6, and he's got 2 sisters as well, and they're thinking of questions as well. Right, Toby, here comes your answer.
OK, Toby, on the outside of your teeth, you've got a very hard material called enamel. That's a sort of shiny white stuff, which is very hard and very good for grinding up food and things. The problem is if you get any tooth decay, then that you get sort of acid from the plaque, bacteria, they produce acid, and that tends to dissolve away the surface of this enamel. Now, if you drink lots of calcium and lots of things like milk, then bits of that can kind of stick back onto the surface and sort of essentially sort of plaster over the holes which you're making, but with all the plaque. And fluoride basically helps that process. So it helps to repair some of the damage which you get from general wear and tear on your teeth and by plaque. If you've got a really badly decayed teeth, it's not enough to do it. But if they're in a pretty good condition, it'll help to keep them that way.
So you've got to keep having your fluoride, please. Ben, thank you very much for your question. All right, let's go to one more here on the email. This is from Dave. First of all, he says, cheapest car, Peugeot 205 GL XD. Also ran on vegetables, so does my 206. Best car I ever had. Vegetables, all right, that's interesting. Let's go like the wind. His question is, how come we find so many oil fields in small pockets so deep under the oceans? And how do we find so many oil fields under deserts? I have read stories about dry wells being replenished as well. Dave, can you shed any light?
Okay, oil, as far basically it's hydrocarbons. It's made by organic matter. So all of the squishy bits of plants and animals and sea creatures, if they get really buried very deeply, and then as they get crushed and over millions of years, and as they get moved close to the centre of the, slightly bit close to the centre of the earth, they get warmed up a bit and they get cooked, and that does all sorts of interesting chemistry. It drives off the water from them, leaving the carbon and the hydrogen forming hydrocarbons. And the hotter they get cooked, the smaller molecules end up. This oil then tends to, if you're deep underground, everything tends to be saturated in water, so this oil floats on water. So this oil tends to seep upwards. And normally, most oil that's produced in the world just then escapes very slowly over millions and millions of years, sort of seeps out of the ground in various places, and it then just bacteria eat it and it gets recycled eventually. However, if you happen to have somewhere with some rocks which will trap it, You can either do that by having rocks which are folded in such a way as you have a sort of waterproof or oil-proof rock, which is folded into a bit of a dome shape. In the middle of the North Sea, it's actually done because there was lots of salt under the North Sea, and salt is less dense than everything else. It tends to float upwards, and you get these salt domes which create little traps at the sides of them which can trap lots of oil. And it gets trapped there, and it slowly builds up until you get enough which it's economic to recover from under there. And so you need the two things. One of them, the reason why you get a lot of oil underwater is that lots of things get deposited underwater. Mm-hmm. So everything's get washed out of rivers with lots of organic material in it, and then they get buried, and they get buried very quickly, so they don't get rotted down too quickly. And so you get lots of organic material buried underwater. So you've got lots of source rocks for oil. And then you quite often get some good clay materials, which make some nice trapping things. Then you get the quite unusual thing of the ground somehow being changed in shape to form a dome-shaped oil trap. And that's what makes oil so rare. Why it's particularly in deserts, I'm not quite sure. Whether it's easier to search for oil in deserts because there's less people to find it. There's less people to get in the way.
Yeah,
less people to complain when you drive around exploding great big lumps of explosive to seismically look for oil. Mm. I think the Middle East is quite unusual tectonically because it's sort of where various continents have collided. So all sorts of strange, the rock has been mashed up in all sorts of strange ways. I know in some bits of the Persian Gulf, there's actually rocks which have been lifted up from incredibly deep, right under sort of below the Earth's crust, have been lifted up onto the surface. So I'd have thought that the very interesting geology there will happen to mean there's a lot of oil trapped there. Mm. I don't think there's anything fundamental why deserts are good for oil. There's fundamental reasons why underwater is good. But.
Mike says, by calling in, he says, I wonder what are optical brighteners and how do they work? An optical brightener, how does it work?
Okay, an optical brightener is, as it says, is something which makes your clothes look brighter. People who, you get them in clothes, washing clothes, you get it in the fibres which make up quite a lot of white things, you get it in paper. They're all over the place. Basically, the manufacturers can't really make these things look perfectly white. They tend to look a bit yellowy. And people think, my clothes are slightly yellowy, I don't want that. So what they do is they put these things called optical brighteners into the washing powders and into the fabrics themselves. When ultraviolet light from the sun hits them, ultraviolet light is a colour of light which your eyes can't actually see. It's just beyond the violet in the spectrum. Mm. And when they hit it, the optical brighteners convert that ultraviolet light into visible blue light. And so you're basically converted invisible light into visible light. So the paper or the white shirt looks even brighter than it ought to. And they're put in all sorts of things. They tend to be sort of organic molecules. There's lots of different ones. We look quite complicated organic molecules made by chemical processes. And they just make your clothes look brighter than they should do.
All right.
Make them glow. You get the same things in fluorescent pens, in highlighter pens.
Oh, yes.
They convert this ultraviolet light into visible light, but with highlighter pens, instead of it always being this kind of pale bluey colour, it can be orange or yellow or green.
Pink.
Or pink. Why not pink?
All right, let's go to the phones again now. We've got Tony on the line. Hello, Tony.
Hello.
Hello, Tony.
Hello, Tony.
We've missed you.
I missed you. I got you on the net, though.
Have you?
I did, yes. You look very nice with the red hair.
Thank you. You try and chat me up, Tony.
You're as pretty as you sound, dear.
Oh, I'm flattered. Well, you're through to the very handsome Dr. Dave now.
No.
What's your question?
Right. In space, if you somehow managed, one of the astronauts managed to break away from the whatever he was doing outside the, is there any way he can get back?
If he pushed himself off the spaceship and he started moving away from the spaceship, because there's nothing to push on in space, the only way he could change his speed would be to take something and throw it in the opposite direction. So this is how a rocket works. A rocket works by throwing hot gases in one direction, and Newton worked out that every action has an equal opposite reaction, or how I like to say, if you push something, it pushes you back. And so if the astronaut, had some tools on him or something...
What about an aerosol?
An aerosol would work beautifully as well. That's a rocket. The aerosol pushes gas out one way, and so he would get pushed back the other way.
Oh, lovely.
And so, you need something to push on. If you're floating in mid-air, then you could push on the air with a fan or by waving your arms around. But in space, there's nothing to push on, so you've got to take it with you. So you'd have to throw something on your person away.
We eat plenty of beans.
That would work too.
Thank you, Doctor.
Thanks, Tony.
Tony, lovely to hear from you. Take care.
Bless you.
Bye-bye. If you're enjoying Ask the Naked Scientist, then you might like to check out The Naked Scientist, our regular roundup of the world's best science. Each week we take a look at the latest science news, talk to top researchers working at the coalface of discovery, and also get our hands dirty with a science experiment that you can join in with too. So make it a date and prepare to strip down science on the web at nakedscientist.com/podcast. Now, Mike has said that he's polishing his shoes because he's got to be presentable for Sue Marchant's big night in. But what happens to shoe polish when you put it on? It's dull and waxy, but then the more you rub it, the more shiny it gets. Why is this? Good question.
Okay, I think it's basically to do with how smooth the surface is. When you put the shoe polish on to start with, it's still quite, hasn't dried out yet. It's quite a soft wax. That means that as you put it on with the cloth or whatever, it's quite rough. And this means if light shines onto it, although the surfaces themselves are quite reflective, because it's such a rough surface, light gets bounced off in all sorts of different directions. Yeah. And so it doesn't act like a mirror, it just acts like a matte, dull surface. Basically, the light goes in all directions. Whereas once it dries out a bit and you give it a good polish, you sort of knock off all the lumps and you smooth it out and you get a very smooth, waxy surface. And this means that if light bounces at it from one direction, all the light which is coming from the light bulb, whatever, will all bounce off in one direction, so it all ends up in your eyes and it starts to behave a bit like a mirror. Just basically because as you polish it, it gets smoother and smoother. If you take a mirror and smash it and make the surface all rough, then it will look white. Because if you imagine a sheet of glass, you get a nice reflection off a smooth sheet of glass. But if you grind it up into a powder, each flat piece of the glass will reflect just as well as the smooth piece. But because they're all reflecting in different directions, you can't see a picture in it.
All right, interesting stuff. Now, John in Peterborough, here's a good one for Dave's lightning brain. He says, how much extra does the Earth weigh in comparison to 2,000 years ago, now that we have all the roads and buildings, etc.? Good one, John. Dave.
Well, if it's certainly with respect to things like roads and buildings, the first question is, where did the stuff come to make the roads and the building? Where did it come from? And that's out the ground. Right. So you take it out of one bit of the Earth. All you're doing is shuffling stuff around, which is on the Earth already. And so it's not going to affect the mass of the Earth at all, because you're just kind of moving stuff from one hole into a building or into a road. The only thing which will affect how much the Earth weighs is if the Earth is losing stuff into space, or if stuff is coming in from space and landing on the Earth. And you do get some of the atmosphere is lost to space all the time. There's sort of plume of atmosphere which is knocked off of what's called the solar wind, which is high energy particles streaming out of the sun, and they drag bits of the atmosphere, very, very upper atmosphere, off very slowly. And also you get lots of little meteorites hitting the Earth very slowly. I'm not quite sure which of these two effects is bigger, so whether the Earth is getting more massive or less massive over time. It was gaining weight or losing weight, but building roads and buildings doesn't affect the mass of the Earth at all.
Well done, Dr. Dave. Mike, the taxi driver. Hello, Mike. He says when he was a child, his granddad told me when lightning strikes, if you count the seconds until the thunder rumbles, every second is representative of a mile. Is this true, and where does this come from? Do you know, Mike, I've been wondering that myself. Dr. Dave.
Almost, very nearly. Okay, if you've got, basically when lightning goes off, you get a huge spark running down from the cloud down to the Earth. You get a huge amount of electricity travelling through the air. That makes the air immensely hot, probably tens, hundreds of thousands of degrees centigrade. When you make a gas very hot, it expands, it's got lots of energy, it expands, and that shakes the air around you. And so the thunder and lightning both created at the same time. Mm-hmm. Okay, now the light from the lightning travels at 300,000 kilometres a second. It essentially gets to your eyes instantaneously. But sound travels at about 300 metres every second, which means that if you're 300 metres away, you'll see that a lightning strikes, then you'll see the lightning immediately, but it will take a second for the thunder to get to you because the sound travels slowly. If you're a kilometre away, it would take 3 seconds. If you're a mile away, it would probably take about 5 seconds. So for every 5 seconds, if it takes 5 seconds for the sound to get to you, then you're a mile away. So almost right.
All right, so it is true. OK, we've got loads of questions coming in. First of all, Michael Barnes says, Dr. Dave, would you accept your own TV programme if offered?
It would be an interesting experience.
So that's a yes then. Yeah, I think it would be an interesting experience. Thank you for that. All right, I'll be your agent and negotiate. It'll be
Sounds good to me.
25%, all right? I need the money. Now then, one here that says, when we say a star is 100 light years away, does it mean that it takes 100 years for the light from that star to reach us? If that's the case, if I looked up to the sky tonight and saw that star, would I be seeing it as it was 100 years ago? And how do we know that if that star hasn't blown up 50 years ago? And so in theory, it's not there anymore, but we still see it.
Good question, and entirely right in all of his thoughts. Yes, if something's 10 light years away, that means it takes 10 years for light to travel that distance. And as far as we know, no information can travel faster than light. So if something is 100 light years away and it blew up 99 years ago, we have no way of knowing that until the light gets here to tell us. And we're discussing Betelgeuse, and recently it's been changing size. The star 600 light years away, and if it has gone bang at any point in the last 600 years, we have no way of telling until the light gets here.
Now, Tony HTV says, Dr. Dave, why is biodiesel only OK in some cars, and why does it thicken in cold weather? Normal diesel doesn't.
I think normal diesel does thicken in cold weather a bit. I know I've heard stories of Russians having to set fire, light fires under their diesel engines to get them hot enough.
Yeah, it's really cold in Russia.
Get in the middle of the winter, it gets really cold, and in order to stop the diesel getting so cold that it if you get diesel very, very cold, it kind of solidifies into a sort of waxy lump, because basically the molecules, they're attracted to each other weakly, and if you get them cold enough, they're not vibrating hard enough to be able to move past each other, and they sort of lock up and form a kind of waxy mess, and they can't flow into your engine. So normal diesel will sort of stop working at very cold temperatures. Biodiesel is not just a pure hydrocarbon. Pure normal diesel is just made out of hydrogen and carbon. Biodiesel's got a little bit of oxygen in it, and that will tend to cause some areas of the molecule to be slightly positive. The oxygen area is probably slightly negative, and this means that the molecules will tend to attract each other slightly more strongly than a straight hydrocarbon. So they'll attract one another more than the hydrocarbon, so they'll basically freeze up and go waxy at higher temperatures. And so it doesn't have to get as cold before you start hitting problems. I'm not quite sure why some engines aren't very good with it. I'm guessing it has slightly different properties. You might need to change the timing. Or it might produce some slightly more nasty byproducts when you burn it, which could damage engines. But if anyone knows, I'd be interested to find out.
All right, me too. If you're interested, then I'm interested. Now, Adrian from Wickham Market says, with the emergence of more wind farms, could you please explain how the wind is converted into usable energy? Thank you very much. How does it work, Dr. Dave?
How does it work? Okay, basically, the wind turbine, it's basically a big propeller. If air blows past the propeller, it causes the propeller to spin. You then you can then attach that to an axle, which is turning. You then attach that to what's known as a generator. Basically, if you move a magnet near a coil of wire, you cause a voltage in that wire. And so basically, in the generator, you've got a load of magnets. They might be electromagnets, depending on the design of the generator, which move near coils of wire. As they move near the coils of wire, that causes electric current, voltage in those wires. And then if you let electric current flow through them, then you've got power, and you can just plug that into the national grid using appropriate transformers and cunning bits of electronics to make it all work.
All right, let's go to the phones this time now. Hello, Peter.
Hello there.
How are you?
All right, very well.
The dog sounds all right as well.
I've got a question to ask. It's relevant to a previous question.
Okay.
Okay. When we stand on the equator, the Earth's going round at what? 1,000 miles an hour, shall we say?
Okay, yeah.
So, when a fighter pilot flies and he goes through G-force, he needs protective clothing, or he needs this So when we stand on the equator, we're travelling at nothing. Or no, when we stand on the poles, we actually travel at nothing. So we've obviously got some sort of protection at 1,000 on the equator. So when we stand on the pole, does it work in reverse, or...?
This is basically why do the jet pilots need such protection to fly at 1,000, but if you're standing on the equator, then it's...
I mean, all we're wearing is skin.
Yeah. The reason why jet pilots need all the special equipment for doing 1,000 miles an hour isn't the doing 1,000 miles an hour, it's going around corners at 1,000 miles an hour. Concorde went about as fast as most jet planes, but it did it in a straight line. And so the accelerations are very small. The problem that a jet pilot has is when you go around a corner, he's changing direction very quickly. And if you're going very fast, you change direction very quickly. That means the acceleration is huge. And the force equals your mass times your acceleration. So if you go around a corner very fast, very quickly, there's huge forces on you, which pulls the blood out of the pilot down to his feet. And then the brain can't get enough blood, and the pilots black out, and you get all sorts of havoc. Whereas if you're standing on the equator, you're doing 1,000 miles an hour. If you only go round, you are going round in a circle, but only once every day. So the speed you're changing direction is very, very small. And that it does have an effect. What it does, that acceleration does have an effect. It tends to get something effectively centrifugal force, which kind of throws you up a little bit, and it reduces your weight by less than 1%, and that is measurable. But because you're going around the corner very, very slowly, it's not a very big effect, and so you don't notice it.
So what would happen if you took somebody from the equator and put them onto the poles then?
Then they would get less than maybe 0.1% heavier. Because they're not being... But other than that, other than getting very cold, not a lot.
Would it affect them?
Oh, if you suddenly change their speed, yes.
Short term, it would affect them.
Yeah, it would be like driving... If you made them stop, if you took someone moving at 1,000 miles an hour from the equator and stopped them immediately, it'd be a bit like driving to a brick wall at 1,000 miles an hour.
Question answered.
But if you slowed them down slowly, then again they wouldn't notice. It's all about change. The problem is changes of speed. The actual speed you're going at actually has no effect on you. It's how quickly you're changing speed or changing velocity.
Peter.
Okay. Thank you very much.
Thank you very much. Bye-bye.
Bye-bye.
Now, Jim in March says, why do aircrafts leave smoke trails behind them, and what is the reasoning for this?
Okay, Jim, there's a couple of reasons. With some old planes, you do actually get black smoke trails because their jet engines aren't very efficient. They don't burn all of the jet fuel, and they leave a load of soot, basically. And you basically get smoke coming out the back of them, and you get a load of black smoke out the back. But what you normally see is the trails. There's two things it can be. The one you see most often is that when you burn jet fuel, you get hydrocarbon that contains carbon and hydrogen. When you burn that with oxygen, it produces, the carbon burns to form carbon dioxide, and the hydrogen burns to form water. So the jet engines are burning an immense amount of fuel very quickly. That produces really quite a lot of water. This water gets dumped into a cold atmosphere when you're high up. And then the air can't hold it because it's very, very cold, and the water condenses to form little droplets, and that's what you see as a cloud. Basically, you see a little cloud forming behind the plane. You can also form trails not without the jet engines at all if you're in air which is almost forming a cloud. There's a lot of moisture in it. And at the wings, underneath the wings, you've got a very high pressure, and above them you've got a very low pressure, which is what's pushing you up. And so the air tries to get around the top of it, and as it gets around the top of it, it starts to spin, and you get a sort of a vortex, spinning air off the end. Centrifugal force pushes the air, sort of throws the air outwards from the centre of those. So the centre of them, the pressure goes down, the air expands, and it gets colder, and you can get moisture condensing in these sort of spinning air, trails of air off the corners of the wings. Which can be quite pretty. But yeah, there's various means, but those are two of them. It's not deliberate. There's no one does it on purpose.
Right, now Pat in Lowestoft says, when you phone your bank, you have to give a reference number. I wondered, now people are getting so advanced with technology, is it possible that someone could listen in on these conversations and steal your details?
I mean, in some ways, this has been possible forever. I mean, people have been able to kind of walk up to your phone line and attach your wires and actually physically tap your phone. And so people have been able to do that ever since phones have been invented. Mobile phones, it certainly is possible to hack into. In fact, there's a big scandal been recently where a newspaper was hacking into all sorts of people's mobile phones and in order to find exciting things about the royals. And they're still getting in trouble with it now, several years afterwards. So it's certainly possible, definitely with mobile phones. Whether it's very common, I don't have any knowledge.
I would think the bank take exceptional and precautionary measures.
I'm fairly sure that if anyone did it, they'd be in trouble.
They would indeed. Now then, Andy, he says, in the car heading home, hope you're well. Yes, thank you very much. On the subject of the universe, it's accepted that the universe is expanding. But what into?
What into? Yes. If we look in every direction, the further we look away, the further things seem to be moving, the faster things seem to be moving away from us. Generally, people, the view is by scientists that the universe isn't expanding into anything. It's just all getting bigger. So the universe is just getting bigger. So imagine it's a bit like if you've got a balloon. You imagine drawing some galaxies on a balloon. And then they start off very close together when the balloon isn't inflated. Then when you inflate the balloon, then the galaxies get further apart because space is expanding as well. So as far as we know, the universe started, although everything was closer together because there was less space and the universe originally started off smaller.
All right, we might be able to squeeze these last few in here. Gerald says there is an infinite number of stars in the universe, yet the night is dark. Why?
That is a wonderful, really fundamental question. And it's because the universe is expanding. If the universe wasn't expanding, it wouldn't be the case. If you're driving past, if you're driving away from something, if a siren, a police car is moving towards you, the pitch is increased and it's getting higher pitched. As it moves past you, the pitch suddenly drops, and as it's going away from you, the pitch gets lower. This is called the Doppler effect. When things move away from you, their wavelength tends to increase. Because the universe is expanding and things a long way away from us are moving away very, very quickly, that means that the wavelength of the light is increased, and it's increased so much that we can't see it. So although if you look in any direction you should see something which was originally very, very hot, the light and really, really white light coming off it, because the universe has expanded so much, the light has been stretched and it's no longer visible, and now it's virtually in the microwave region.
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.